Hi folks, we are on Unit 4, Day 2, and today we're really going to get into one of the big ideas that is kind of foundational to what we're going to be doing with calculus. So this is sort of the start of that new material, and we're going to be talking about limits. So a limit is a mathematical concept that sort of describes what happens as a value gets closer and closer to something. It's different in pretty much all of the math that you've ever done has been finding what happens at this point. With limits, we're talking more about what happens as you get close to a point, not actually what happens at that point. So just kind of a thought experiment. Is it possible to continuously move the dot halfway to the wall? So if you were, say, like a meter away, could you move, so you're half a meter away, and then half that distance you're moving, so you're a quarter of a meter away, and then an eighth of a meter. And can you get closer and closer? Would you ever touch the wall? Now, we know that obviously in real life that would happen. But when we start thinking mathematically, kind of with the concept of infinity and distances getting infinitely smaller, what does that actually mean? So a function where we could talk about this, here's some function, looks vaguely polynomial, where we have a whole at x equals 4. Can you find the value of f at 4? We can't because of that hole there. It's undefined. But can we say what's happening to the function as we get closer and closer to 4? Sure. We could say we could find the value at 3.9, and we could find the value at 3.99. and 3.99999, and we could keep getting closer and closer and closer and closer to 4. As long as we don't actually hit that 4, we can keep getting what's called arbitrarily close, or sort of infinitely closer to the value that does not exist. So that can be really useful in describing this function. So we could say, I need to count here, 1, 2, 3, 4, 5, 6, 7, 8. So as we move closer and closer to x equals 4, the y value moves closer and closer to 8, even though that one individual point where x equals 4 doesn't actually exist on this function. But we can say as x gets close to 4, or closer to 4, y gets closer to 8. And that's really what a limit is. That's talking about what is happening to the y value as the x value is getting close to something, not necessarily what's happening at that actual point. But this description, as you get closer and closer to 4, the y value is going to get closer and closer to 8. That's really valuable to know about the shape of this function. So here's a more mathematical definition. If f at x becomes close to a single value L as x approaches, that arrow means approaches, C from both sides, then we write, and here's our notation, the limit as x approaches C of f at x equals L. So that's is or equals. So the limit as x approaches whatever this value is, usually that would be a number, of the function, it equals that value. Okay, so in the previous slide, so if we were looking at that previous graph, we could say that the limit as x approaches 4 of f at x equals 8. Because as x got closer and closer to 4, the y value got closer and closer to 8, where that hole was. Now there doesn't have to be a hole for us to be able to find a limit at a point. So here, given f at x equals 2x plus 1, we want to find the limit, so the limit as x approaches 2 of f at x. So what happens on this graph as x gets closer to 2? Well, that's just a line. So, okay, let's sketch it out and kind of think about what this means. Sometimes people get very wrapped up in the idea of limits as describing holes, and they are super helpful for sure to be able to describe behavior around discontinuities like a hole, but they can be used to find any value, even ones on kind of nicer, simpler functions that don't have that kind of messiness happening. So I'm going to graph the graph of f at x equals 2x plus 1. So I've got a line with a slope of 2 and a y-intercept of 1. And I'm just going to draw this graph in there of f at x. So this limit here is asking us, what does the y value of f of this graph, what does f at x approach as x approaches 2? So as we're going towards 2, what's happening to my y? As I kind of slide along this graph of this line, as I'm going closer and closer to 2, y is getting closer and closer to 5. It actually ends up equaling 5. But we know that this is a continuous function. So the limit as x gets closer and closer to 2 is just going to be 5. So it's 2 times 2 plus 1, which is 5, which makes sense, right? As you move along this line towards x equals 2, the y value is going to get closer and closer to 5. It's okay that it actually equals 5. Lots of times it is continuous and you do have a function defined there. It doesn't necessarily have to be a hole, although those ones are more interesting. So that tends to be what you see more of in the homework questions on limits. That's why I think sometimes people get mixed up and think that limits only happen around holes. They happen everywhere. You can evaluate limits lots of different places, not just at the hole of a function. But like I said, that previous example was kind of trivial because it's just a line. The value of the limit, there's no holes, there's no funny business happening. It's just going to be the value of the function. Here, however, we've got this function here, and we want to find the limit as x approaches 5 of g at x. Now, what do we see? In a rational function, this is what I mean by this one's more interesting. In a rational function, I do actually have a restriction on the function that x can't equal 5. So I'm going to have to do some math and say I'm going to find the limit as x approaches 5 of x squared minus 25 over x minus 5. And I can see right now that if I substituted in 5, I would get a 0 on the denominator. So I can't do that. But sometimes you'll be able to simplify first. And in this case, obviously, I would put in 5 on top and also get 5 squared minus 25. So I'd have a 0 in the numerator as well. So what I'm going to do is the limit as x approaches 5, and I'm going to factor. And we can do this because we're not talking about find g at 5. I'm not asking what the value of the function is at 5. So I don't have to pay attention with limits to the restrictions. I'm allowed to have the limit as x approaches 5, even though that was a restriction on my original function. So the limit as x approaches 5 of x plus 5 is 5 plus 5, which is 10. So what that means is that if we graph this, and I don't think I have the graph of this on the next page. If I graph this, this actually ends up being a linear function because I can reduce that with a hole or a restriction at x equals 5. So this is the graph of that function. It's a line, y equals x plus 5. So I'm just going to kind of roughly sketch this in where there's a hole at the point 5, 10. So the limit as x approaches 5, if you're moving along this line, getting closer and closer to that hole, your y value is getting closer and closer to 10. We won't have a value of g at 5. G at 5 is still undefined, but we can talk about what's happening around that as we get closer and closer and closer, and that's what limits are helpful for. So that previous example is what's called an indeterminate limit. If we substitute in and we get something that's 0 over 0 or infinity over infinity. So for example, in that last one, if we had subbed in the 5 right off the bat into the original function, we get 0 over 0. And that means that the limit is what's called indeterminate. It doesn't mean that the limit doesn't exist. It just means that to find the limit, you have to do some more math. Sometimes those limits don't exist, but oftentimes you can simplify the value of the function, do some simplification, and be able to evaluate the limit. Because remember, we don't have to kind of abide by restrictions when we're talking about limits, because we're not talking about the actual value of x equals 5. We're just talking very, very close to it, which was okay. So a similar kind of example, we have the limit as x approaches 0 of x squared plus 4x. So I can kind of visually see that if I subbed in 0, you don't have to show this if it's, fairly obvious. If I subbed in 0, I would get indeterminate. So I get an indeterminate of 0 over 0 if I just subbed in right off the bat. So I have to do some math. I need to keep this limit notation. If forgetting to write vector signs was the big communication error people make in the first half of this course, forgetting to keep writing your limit notation is the common error in the calculus half of this course. So that is really, really important. We're not talking about just the function here. We need to keep that limit notation up until we substitute something in. So here, if I factor out an x on the top, I can reduce. So then this is the limit as x approaches 0 of x plus 4. And then when I substitute this number, now it's not indeterminate. Now I can put a 0 in. That's when I drop the limit notation. So I'm going to kind of make a note here. Only drop the limit as x approaches something when you actually sub it in. Okay, so you cannot just take away that limit. That's a big communication issue for sure if you forget to keep writing that. And you wouldn't keep writing it here because it's not the limit as x approaches 0 of 4. It's just the actual value. You've already evaluated the limit. So in this example, this is kind of the opposite case. Sometimes people see a rational function and right away think, oh gosh, I got to factor that and simplify because it's going to be indeterminate. Not necessarily. So think about what's going to happen if I sub in x equals 0 here and get 0 plus 0 plus 3. Okay, 0 plus 0 plus 1. Those aren't 0. So you don't automatically have to factor and simplify just because you see a fraction. Sometimes people kind of see that right away. And sometimes people, if it doesn't reduce, get very stressed out and say, oh, I can't evaluate it. This one's even easier than the last one. You can just evaluate this limit because it's not indeterminate. So I don't have to simplify. I'm just going to evaluate this by substituting in the value of c equals 0. So I'm dropping the limit notation right away. And I just get 3 over 1, which is 3. So this wasn't a hole at all in my function. It wasn't a hole. It wasn't an asymptote. It wasn't a restriction. I can just evaluate the limit as x approaches 0. Because that function was continuous at 0. So whatever x was approaching there was just the value of that function. The next big idea we're going to talk about are called sided limits. So this notation here is going to, just going to find a highlighter here, is going to involve notating with a plus or minus if we're talking about a specific limit from only one side of the function. So if you're talking about the limit on the left side of the function, you have a little minus because that's like towards the negative side of the function. And if you have, if you were thinking about the x-axis, if we have a plus sign, that means we're evaluating the limit coming from the positive side or from the right side of the function. So an example of this might be a function like this, 1 over x minus 3, where we have an asymptote. So we'll start off just with a sketch of f at x equals 1 over x minus 3, and that's going to be the function 1 over x with a shift 3 units to the right. So here's my graph. So we see that we've got that rational function shape, and we have an asymptote at x equals 3. So if here we were evaluating the limit as x approaches 3 from the left, what's happening if we're on the left of 3 and going along, tracing along that graph, what is the y value approaching? As you get closer and closer to 3, you get bigger and bigger in the negative. So you're approaching negative infinity. You're going, as x gets closer and closer to 3 from the left-hand side, the y values are going down, 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 big into the negative numbers towards negative infinity. And as x approaches 3 from the right-hand side, we're going up and up and up and up. So here we're increasing towards positive infinity. So the limit as x approaches 3 from the right-hand side, or the positive side of that, we are approaching positive infinity. Now, what does it tell us if we get these different sided limits? And kind of in general, not just with negative and positive infinity, but we often see this with piecewise as well. If you're going from the left and you're going to one value, and you're going from the y and you're going to another value, that means that that function's not continuous. It's not approaching the same from both sides, it's disjointed. So that's going to tell us something that we'll get more into later in this unit about the continuity of the function. But for now, what we're going to say is that these sided limits have to exist for us to be able to say the limit in general. If I popped back to that graph of y equals 1 over x minus 3, could you say what the limit as x approaches 3 of f at x is? Could you tell me what that would be? You couldn't, right? It would be depend on what side. Down here it's negative infinity, and up there it's positive infinity. So it does not exist. So the limit doesn't exist because it's different on both sides. And that's what this is saying in kind of more mathematical terms. If f is a function and c and l are numbers, then the limit as x approaches c of my function f at x equals L if and only if. Remember that we've talked about that in the vectors. If the limit from the left equals the limit from the right, and that would equal L. So if the sided limits are equal. So if you don't have the limit from the left equaling the limit from the right, you can't evaluate the limit overall. Because if the left-hand side is going to one spot and the right-hand side is going to another spot, we can't say what those limits are. They're different. So there's no overall limit at that point. So the limit as x approaches c of f at x exists if and only if those sided limits are equal. So we need to have the sided limits be equal, and that means the limit exists. If we know the limit exists, then we also know that the function must approach that value from both sides, approaching the same value. So remember the if and only if. If we know that the limit exists, then we know both sided limits are equal. If both sided limits are equal, then we know the limit exists. So that's a both directions theorem. So in our example, I already wrote this on the graph, but that means that this limit as x approaches 3 doesn't exist because the sided limits are not equal. So here we've got another piecewise function. So this is one of the reasons we reviewed that in day 1. So we have f at x equals x squared, so a nice simple parabola for x greater than 0. And we have f at x equals -1 for x equals 0, and f at x equals x minus 2 for x is less than 0. So what we want to find is the limit as x approaches 0 of f at x, and see what we see here. So I have done a graph of this. So for values bigger than 0, I'm just going to kind of fill that in because I don't know if the yellow there is going to show up very well for you. Okay, there's my function. For values greater than 0, we've got this parabola. Less than 0, we have that line y equals x minus 2. And these are holes because it's a strict inequality. And then we have that point where y equals -1 if f equals 0. So we could say, I don't think I have, yeah. We would have to look at the limit as x approaches 0 from the left of f at x. So as we're approaching from the left, if we're on the left-hand side of 0 and we're going towards 0, the limit here would be -2. It's getting closer and closer to -2. And if we were approaching from the right-hand side, so the limit as x approaches 0 from the right of my function, you have to see what you're taking the limit of. Sometimes people leave that part out. So if we were on the right-hand side and kind of moving along the function towards x equals 0, we're getting closer to a y value of 0. Okay, so obviously these are different. It's approaching different numbers, different values from one side or the other side of the 0. So we could say since the limit as x approaches 0 from the left of f at x is not equal to the limit as x approaches 0 from the right of f at x, you need that function in there, then the limit as x approaches 0 of f at x does not exist. So we can have these individual sided limits exist. We can evaluate those, and that can be a question in your homework or on a quiz or a test. But you may not necessarily be able to have a limit overall existing. So the sided limits might exist, but unless they're equal to each other, the limit itself does not exist. Okay, one last example here. We do a lot with factoring, especially initially, but it's not always factoring. Sometimes it's other ways of simplifying. So here, if we put in an x equals -1, we would get -1 plus 1, which is 0. And on the denominator, we get 1 plus 1 over -1. So that would be -1. So 1 plus -1, that would be 0. So this is an indeterminate. And in the next lesson, actually, we're going to look at a lot of different ways we may have to simplify indeterminate limits to be able to actually evaluate them. But this one, I really don't like that fraction within a fraction. So I'm going to try to clear that out. And there's different ways people could approach this, but I'm just going to multiply the top and bottom of this by x over x. So I would get x squared plus x over x plus 1. And now I can factor. So you may not have like just a straightforward rational function, but now I see I can factor and reduce that. So this would be a restriction on my original function, but it's not a restriction on the limit, because the limit isn't talking about the function actually equaling that point. It's just talking about what happens as you get closer and closer. So now, remember, I'm keeping this limit notation all the way along through my work until I'm ready to substitute in. And now that's been simplified enough, I can just substitute in that -1, and I'm all done.